Alright, so now I want to explain another beautiful article which uses variational autoencoder, and this is done by great people. I know Graham Neubig is a great researcher in Carnegie Mellon, and if you like this article with high probability, you also like this article, and this article. So what is this structVAE? They use variational autoencoder and for semi-supervised semantic parsing. The reason is that whenever we see nowadays, well, it's not a good generalization. So when the reason that they use semi-supervised semantic parsing is because, first of all, supervised learning, we have small data for supervised learning, especially in language domain, that we have scarcity in some languages, and so or some semantic parsing, because the task of semantic parsing is really challenging, and it needs crowdsourcers cannot do that. They should be very highly educated, and so first of all, labeling is expensive, and second of all, we can take advantage of all unlabeled data. Like in language modeling, why do we like language modeling? Why ChatGPT is popular? Because they use unsupervised learning, because we have access to infinite amount of data. So in semi-supervised learning, here we use the framework of variational autoencoder, and we take these trees that are generated as Z, and Z is our latent variable, because we don't, for example, we assume that we don't have access to them, especially the highest probability, the highest probable tree. And so it's the same framework, the same paradigm that we have used for images, now we used for text and sentences. So Z is our semantic tree, and when we use this word structured here, it's just there is a graph structure. You see, the parsing is like a tree, and tree is a type of graph, and so it's a variational autoencoding model for semi-supervised semantic parsing, which learns both from limited amount of parallel data and also readily available unlabeled natural language utterances. So this Z, as I said, it models latent variables that are not observed in the unlabeled data, and it's a tree structure latent variable. They use it for both HEIS domain and also for Python code generation, which is really amazing task. So you give some utterance and it produces the Python code just using this algorithm. You can implement it and enjoy it, especially if you are a Python programmer. So structVAE is a variational autoencoder. And the surface natural language utterances are generated from tree structure latent meaning representation following the standard variational autoencoder structure. An off-the-shelf semantic parser functions as the inference model and parsing an observed natural language into latent meaning representations. And the reconstruction model decodes latent MR into original observed utterance. So just like in computer vision that you have an image and you use variational autoencoder, here you have representation Z, which is something, and you're using, for example, Gaussian random variable, and then you reconstruct the original, so X is an image, you reconstruct the original image, and we want X and X tilde to be as small as possible, this difference. So with the same intuition, they are using it for utterances. So we have a natural language utterance, so you encode it, but they're encoding, so it produces a z variable. Your z variable is that semantic parsing, that meaning representation. It could be hybrid tree, it could be any tree that you like, that you enjoy. And then once we have this latent variable, we can generate the original natural language utterance. So natural language at the output, we want to minimize this. So this framework of variational autoencoder, you see, can be applied to both images, here for natural language, you can use it for speech, for music, any type of data or financial data that I've used several years ago, or even you can use it for data mining, you can use it for hiring. So this variational autoencoder could be applied on any type of data. So I explained this, and now structure variational autoencoder, we implemented transition-based semantic parser. I said that Z is a latent variable, your parse, but you could generate it in several ways. You could use graph-based algorithm and use a structVAE algorithm for inference. But the simplest things, the fastest things is transition-based. And no matter if you're top-down design or bottom-up design, transition is fast. Of course, top-down design could be risky, but bottom-up design, like a traditional constituency parsing, is much safer, and but doesn't matter. We use transition-based to generate these trees, but now usually, especially Neubich, the author, usually likes to use abstract syntax trees because they are really flexible, they are easy, they are very good if you want to work with these programming languages. So it can represent that, for example, sorted of my list and then reverses through the argument, the keywords, the arguments, and the function that you're using. Then you can evaluate. So this, for example, sorted of my list and reverse can be represented by this abstract syntax tree. So our meaning, when we say meaning in this paper, it means this abstract syntax tree. But you can write another paper with your favorite representation or formalism. But the framework of variational autoencoder still holds. You can take advantage of that. But it's very interesting. Still, unsupervised learning is the hardest problem in all of the machine learning community. Maybe human-centered AI and reinforcement learning, interaction-based in general, could help. But it has a lot of technical issues, as well as some problems of your paradigm that you are using. So this is an example of abstract syntax tree and uses AST. So traditionally, purely supervised semantic parsing using parallel data and annotated data, we don't always have these meaning representations. For each utterance with X, we don't have Z of that, we don't have meaning of that. It's expensive, as I said. That's why we use some supervised data, maybe 1,000 or 10,000 training data points. But mainly we are relying on this unsupervised world, which is really free. And that's why the all success of ChatGPT and those things is just because the data is free. You can just do web scraping with Python, Java, and get lots of data and then training. So there is a trade-off. So alpha is a trade-off between how much you unsupervised world you want to use and how much supervised data you have. So it depends on your budget. And the rest of that is really standard. You use here you just use abstract syntax tree. And in abstract syntax tree, we are using ASTL grammar. For example, apply constructor action, action apply constructor to the frontier composition field. And expanding the derivation using the field of C. Or reduce action complete generation of field with optional or multiple cardinalities. Gen token V action, this action populate an empty primitive frontier field with token V. So we are modeling this queue using this sequence to sequence network, because we have X, we have a sequence of X, your utterance, X1, X2, and the length of your sentence could be N. And so you can give it to another LSTM, which could be, or GRU if you want it to be faster. And so it models the sequence for Z if it is linearized. So this hidden representation of this Z that you are given, so it's just autoregressive. So it's just traditional sequence to sequence. You can use it to model Q. So given X, you can predict your latent variable. Your latent variable here is your abstract semantic tree. Abstract syntax tree, AST. And so I said this supervised learning, but this supervised learning can be written in this way. Because you can also take advantage of, you know some Z, condition on Z, you know what is you want to maximize the probability of your utterance. You can take advantage of that. Or instead of just P of Z given X, you can use it like this because you take advantage of reconstruction model as well. So for unsupervised learning, you see in all texts it is very common that use variational lower bound, and so we maximize the variational lower bound. And KL, is KL divergence. I've explained it in my playlist for machine learning ideas. It's a very basic measure of similarities, and lambda is just a tuning parameter. You want to say how much and P here is just you can define a prior and say how much it is close to that as well. Because anyway, you have some prior knowledge of your meaning representation, your abstract syntax tree. You can say that this Q, because it's so general, we don't want it to go anywhere. And of course, we are talking in the space of functions. So we don't want this to be everything. So we bound it by keeping as close as possible to your prior of abstract semantic trees. And this is another technical thing that we see in all papers. They use, they approximate this derivative of loss with respect to the parameter using the reinforced algorithm. So whenever I see this as a reward, if you like this reinforcement learning, you can look at it in different ways, So we define the learning signal as this L could be L prime minus B, and B is just A log plus C. This is motivated by the empirical observation that log of your probability correlates well with the reconstruction error log probability of X conditioned on your latent variable. And finally, this can be computed like this. So this is a supervised term. The supervised term consists of two terms. And these are the experiments for if you just purely focus on supervised approach, or you just or this article, which is called this model is called structVAE autoencoder. The reason that you see these accuracies are low is just because, well, you're using semi-supervised learning, and it's challenging. So that's why I really like any article on unsupervised, because each article on unsupervised learning can improve state-of-the-art achievements. And this is an example of natural language, and it's tree. And Z, for example, as I said, is abstract syntax tree, and for Python automatic Python code generation. And you see that this is, for example, true, but this is not true. And you can see the probability of each utterance given your latent variable, as well as the probability of your latent variable condition on X. Another beautiful example is this. You have some surface natural language utterance. For example, you say, define the method init with 3 arguments: self, unpack, list. We are already in the future. We are speaking in English, and the code is already generated. So you can do it for yourself and enjoy that. Or if you are working in your company, you can just create this automatic Python code generation for your PyTorch codes or any project that you are working on. So you see latent meaning representation and the surface natural language. For example, this one is interesting. Show me the latest flight from CI0 to CI1 that serves lunch. And it can easily generate this code. What is the argmax and meal from? It understands that it is related to departure time with this argument, the first argument. So the prior is a standard LSTM language model. We use the sequence representation of Z. So, for example, what is the probability of a syntax tree, abstract syntax tree? And because it's a LSTM language model, you can use this simple approach. We use LSTM to generate these things. And for a reconstruction model, we use attentional, because now we have, as I said, first you should generate with Q, which is inference model. You have an X, it produces Z. And then you have Z, it reconstructs the original utterance. So reconstruction model is X condition on Z. So reconstruction model is P of theta, this one. So this part is also again like attentional sequence to sequence model, because Z is a sequence. You give it to X, which is a sequence, and we use attention, soft attention, to know which the alignment of the words that should be concentrated to produce X. And you can use this probability of